Hello everyone, my name is Tsepenekas and I will continue our discussion on concepts of demographic fairness for clustering. Now I would like to talk about demographic fairness when clustering with outliers. So let me begin with a brief summary of what clustering with outliers is. In this setting, again, we have a set of points in a metric space which is characterized by some distance function d. And once again, we need to choose a set S of at most k cluster centers. In the example here on the right, the two black points correspond to the two chosen cluster centers. However, in this model here, we are not required to cluster all points of the dataset, and we can rather choose a set A of points to cluster. And this set A should contain at least m points, where m is some given inc parameter. In the example on the right, the green points, together of course with the two chosen cluster centers, are the points that we decided to cluster, are the points of the set A. Now, since A contains the points that we need to cluster, that we decided to cluster, we also need to construct an assignment function phi that will map every point of A to one of the chosen cluster centers, thus creating a collection of at most k clusters. In the example on the right, I'm denoting the assignment with arrows. So for instance, this green point over here is assigned to this cluster center. And you can see that we have two clusters, one over here to the left and one over here to the right. And obviously, we construct this assignment function in a way that optimizes some objective function. For instance, let's say that we want to optimize the k-means objective function. As you can observe, in this model, we are allowed to exclude some points from our computations, and by that I mean leave some points unclustered. Now, the points that are going to be left unclustered are called outliers, and in the example on the right, the three white points on the perimeter are the chosen outliers. The question here is, why do we need to consider models with outliers? Well, there are multiple reasons for that. A very good reason is for the sake of robustness. When we care about robustness, we basically interpret outliers as noise in the dataset, noise that we want to exclude from our final clustering solution. Another good reason for considering models with outliers becomes evident when we view the problem from a facility location perspective. In a lot of facility location applications, we only have a limited amount of resources, and this limited amount of resources may not be adequate to provide good service to all the points of the population, and therefore it might be acceptable to only focus our attention to providing good service to a fraction of the population instead of providing poor quality service to all points in the population. I would also like to give some more concrete motivational examples for clustering with outliers. The first such example is a classical clustering setting in which the points correspond to users of an e-commerce website, and the website wants to cluster its users into groups of high similarity, with its end goal being developing a recommendation system. So here, users that are placed in the same cluster are deemed similar enough, and therefore they will be given the same type of recommendations. In such example, it might be acceptable to exclude users with very unique profiles from our clusters, and it might make sense to do so, because if we end up including these users in our clusters, then in our solution, the intra-cluster similarity will be pretty low, and therefore the quality of recommendations we end up providing to the points will also be low. Therefore, for the sake of providing good quality of service to our points, we choose to consider a model with outliers. Another application here comes when we view the problem from the facility location perspective. And here, points will correspond to physical locations in some metric space. For example, points may be cities, towns, neighborhoods, or even the houses of individuals. Now, in this setting, suppose that we have a state that wants to allocate vaccination centers in the metric, such that every point, every location has close access to one such vaccination center. However, the resources available to the state might be quite limited, and therefore the state might not be able to provide good access to all points of its population. If that's the case, it might be acceptable for the state to only focus its attention to providing good access to a fraction of the population instead of providing poor quality service to everyone. Now that we saw what clustering with outliers is, let's also see how demographic bias naturally arises in this context. For that, we need the following very crucial observation, and that is that being chosen as an outlier is an inherently disadvantageous event for a point. And let's give some examples that demonstrate this. At first, recall the recommendation system application. There, points that are chosen as outliers will not receive any recommendations at all. Now, recall the vaccination center application. There, points that are chosen as outliers are not guaranteed close access to a vaccination center. And therefore, you see that being chosen as an outlier implies more or less that you are denied service. So the question becomes, what should we do when our input set of points consists of multiple demographic groups, let's say gamma demographic groups? And I have an example here on the right with two demographic groups, the red points and the green points. And now, in such a setting, in a setting with multiple demographic groups, we can see that the solution which disproportionately chooses outliers from certain demographics only can arguably be considered unfair. And let's see this solution. This solution chooses two cluster centers, this one over here to the left and this one over here to the right, and assigns all red points to these cluster centers while leaving all the green points as outliers. This solution is blatantly unfair to the green demographic. So, how can we mitigate that? How can we address such scenarios of unfairness? Well, in the fair variant of clustering with outliers, at first, in the input, we have a positive integer value ML for every given demographic group CL. And now, instead of asking for clustering at least M points, we rather ask that our set of clustered points A contains at least ML points of every demographic group CL. So basically here, we want to guarantee that we cluster at least ML points of every given demographic CL. And let's see how this new fairness constraint can potentially fix the previous unfair solution. So I have the unfair solution here to the right, and let's assume that in this example, in this instance, we run an algorithm that satisfies this novel fairness constraint. And let's also suppose that the lower bounding M value for the red demographic is 5, and the lower bounding M value for the green demographic is 2. Then, in such a case, if we run such an algorithm, we might end up with a solution that looks like this, and observe that in this new solution, even though the objective function cost is worse because the assignment distances now are larger, this solution is no longer unfair. And it is no longer unfair because it doesn't completely or disproportionately ignore the green demographic. Another interesting aspect of this model is that the input parameters ML are arbitrary, and this is actually a good thing. And it is a good thing because it allows us to capture a wide range of fairness scenarios. So for instance, we can capture an equitable treatment case. In equitable treatment, we want to guarantee that the same fraction of points will get clustered for every demographic. So let's say that we want to guarantee that at least half the points of every demographic get clustered. Another interesting scenario we can capture, and perhaps a more intricate scenario, is preferential treatment. In preferential treatment, we want to focus our attention to demographics that, let's say, are in a higher need of help. And to those demographics, we will provide a larger ML value, and therefore we will end up clustering more points from those demographics. Now, a good example, a good motivational example for preferential treatment here comes when we think of the vaccination centers application. There, let's say that one of the underlying demographics is senior citizens. then it makes a lot of sense to guarantee that almost all of the senior citizens have close access to a vaccination center, and you do not leave a lot of them as outliers. Now, the fair variant of clustering with outliers has only been studied for the case center objective function, and in the literature, this problem goes by the name of fair colorful case center. This problem was first introduced in an ISA 2019 paper, and the authors of that paper gave a 17 approximation algorithm for it. Now, this algorithm only works when the underlying metric space is the Euclidean plane, and again, it only works when the number of demographic groups gamma is a constant. Later on, at TIPCO 2020, there were two papers that independently studied this problem, and both of them gave improved constant factor approximations for it. Most importantly, both of these results work for arbitrary metric spaces and not just for the Euclidean plane. However, again, both of these results only work when the number of demographics gamma is a constant. Nonetheless, one of these two papers, one of the IPCO papers, the Aneg et al. Paper, also shows that when the number of demographic groups is not a constant, that is, when the number of demographics grows with the size of the input, then in that case, we cannot devise any approximation algorithm for the problem, unless, of course, P equals MP. Now, this concludes everything I wanted to discuss with regards to demographic fairness when clustering with outliers. Now, let's move on to the last concept of fairness that we will see in this tutorial. And this concept of fairness is called socially fair K-clustering. The starting point here is the following very important observation. And that is that in almost all clustering and facility location applications, the quantity that really matters to a point is the distance to its assigned center. And this quantity, the assignment distance, matters because it reflects the quality of service that the point receives. So, in classical clustering applications, the assignment distance corresponds to how representative the cluster center is for a point. And in facility location applications, this quantity corresponds to how far the point needs to travel in order to find its service provider. Therefore, the smaller the assignment distance, the happier the point. And let's see some examples that demonstrate this. At first, recall the recommendation system application. There, the smaller the assignment distance is for a point, the more representative the assigned cluster center is for the point, and therefore the more suitable, the more fitting the recommendations that the point receives. Now, recall the vaccination centers application. There, the smaller the assignment distance, the less time the point needs to travel in order to find its assigned vaccination center. Okay, given this realization now, that is that the assignment distance is of utmost importance, the question becomes, what should we do when our input set of points consists of multiple demographic groups? If that's the case, then it makes sense, it's reasonable to seek solutions where, for each demographic group, the assignment distances that we provide to the points of this demographic are fair with respect to the assignment distances we provide to points of other demographic groups. And let me give you an example that clarifies this statement. This is an example of an unfair solution, unfair with respect to the assignment distance being of utmost importance. So, in this example, we have two demographic groups again, the red points and the green points. And we have a solution which chooses as cluster centers this point over here and this point over here. Arrows again denote assignments. So we have two clusters, one to the left and one to the right. And let's assume that the length of the arrow corresponds to how large the assignment distance is. So the larger the arrow, the larger the assignment distance. In other words, we are in R2, we are in the Euclidean plane here. Okay, observe now that on average, the assignment distance of the green points is much larger than the assignment distance of the red points. And therefore, this solution can be considered unfair to the green demographic. So, again, how can we mitigate that? How can we address such scenarios of unfairness? This is exactly what socially fair K-clustering tries to do. In this problem, as always, we need to choose a set S of at most k cluster centers and subsequently construct an assignment function phi that maps every point to one of the chosen cluster centers, thus creating a collection of k clusters. Now, before I proceed to the fairness requirements of this problem, let me give you some notation. Suppose that we have a solution, then for that solution, we denote by delta L the average assignment distance of the points of demographic group CL. So this is just a weighted sum. Now, the fairness goal of this problem of socially fair K clustering is to minimize the maximum average assignment distance over all demographic groups. And let's see how optimizing this objective function can potentially fix the previous unfair solution. So the previous unfair solution is here to the right. And now let's assume that we run an algorithm that optimizes this objective on this example. Then we might end up with a solution that looks like this, and observe that in this solution, the average assignment distance of the green points is more or less the same as the average assignment distance of the red points. And therefore, this solution can be considered much more fair compared to this one over here. Finally, another interesting aspect of this model is the way it incorporates fairness considerations in the specifications of the problem. Unlike most problems that we saw so far in the tutorial, this problem over here does not incorporate fairness in the form of a constraint. It rather incorporates fairness in the form of an objective function, an objective that we try to optimize. Now, this problem, socially fair K clustering, was independently introduced by Gadiri et al. And Abbasi et al. And both of those papers appeared at FACTA 2021. Both of these papers give an O of gamma approximation algorithm for the problem, and recall that gamma is the number of demographic groups. Later on, at COLT 2021, Makaritsev and Bakilian gave an improved log gamma over log gamma approximation for the problem, and they also argued that this approximation ratio is the best achievable for the problem under some specific assumption for hardness. Finally, we have a relatively recent result of Goyal and Jaiswal, and this result is a 3 plus epsilon FPT approximation algorithm. This is a fixed parameter tractable algorithm, and the fixed parameter here is the number of cluster scale. And this concludes everything we wanted to discuss with regards to demographic fairness for clustering. Thank you.